The concepts of a basis and the concept of a dimension both can be relevant for subspaces as well. Okay? We have a subspace of a vector space. We can ask, what's its dimension? Okay? And its dimension is going to be the number of elements in a basis for that subspace. And a basis is still going to be a set that spans only the subspace and is linearly independent. Okay? So let's start by doing some examples. That's always a good way to relate to concepts, to do examples. So example number 1, we're going to take our space to be 2 by 2 matrices over R. And what's the dimension of V?
4.
Right, the dimension of V is 4. We know that. Everybody? Sure? Okay. And here's a subspace of V. I'm going to call it U. U is going to be all the elements in V. I'm calling them capital A because elements here are matrices, right? So all the A's in V, satisfying that A equals A, B, minus B, A plus B, where A and B are scalars. Okay, so U is the set of all the 2 by 2 matrices. Satisfying that, the matrix is of a specific form. Okay, so just a side remark, this is a standard way of defining a subset of a set, okay, by imposing some conditions on the elements. Okay, so I'm only taking those matrices that satisfy certain constraints, certain conditions. That if you have B here, that you're going to have minus B here. Okay, and then here you're going to have whatever sits here plus whatever sits here. Okay, and in order to define a subspace in this manner, it doesn't really have to be a subspace. It could be any subset. Okay, if I want to define, for example, all the students in this class, that's a set. And a subset is going to be all the redheads. All the students whose hair is red or orange or anywhere in between. Okay? So that's a way of defining a subset by listing a certain number of constraints on the elements. Okay? And I'm emphasizing this because in example 2, we're going to define a subspace in a different way, which is unique to subspaces and cannot be done for subsets. Okay? So is it clear that defining by listing some restrictions is good for any set? Not necessarily a subspace. We didn't use the fact that we're living in a vector space to do this. Okay, good? Okay, so here's a spanning set for U. So the set containing the matrices 1, 0, 0, 1 and 0, 1, negative 1, 1. This set of 2 matrices is a spanning set for U, for the subspace. Why? Because any element in U, since any element in U, A, B, minus B, A plus B, that's the form of a general element in U, it can be written as a linear combination of these two guys. That's why I chose them as A times this plus B times this. Do you see that? Equals A times 1, 0, 0, 1 plus B times 0, 1, negative 1, 1. Do you agree? Everybody good? So this is a spanning set for U. Is it a basis for U? Well, we have to check if it's linearly independent. And are these two guys linearly independent? Yes, they are, because there's only 2 of them and one is not a scalar multiple of the other. right? So that's one way to say it. If you really want to, you can straighten them out in rows of a matrix, and it's already in echelon form, and there's no zero rows. Okay? So this is a spanning set for you. Let's give it a name. Let's call it B. Let's call it B sub U. B for basis, U for the what it is a basis of. So B sub U, BU is also linearly independent, and therefore BU is a basis for U, implying that what is the dimension of U? 2. Because we found a basis with 2 elements. Good? Okay. Here's another example. Let's take V to still be the 2 by 2 matrices over R. Same ambient vector space. And let's take W to be the span of 3 guys. 1, 2, 3, 4. 1, 0, 0, 5. And 1, 4, 6, 3. So W is the span of these 3 matrices, namely all the linear combinations of these 3 matrices. Okay? So this is another way of defining a subspace in a vector space, which would not work for a subset. I cannot define a subset of the students here as all the students that are linear combinations of U, U, and U, because it's not defined. What is a linear combination of students? Okay? Clear? So there are no operations on a set, and therefore you can't do anything in the form of generators. You can only do that when you have operations, like in a vector space, or in a group, or in a field, or anywhere where you have operations. Okay? So what is going to be the dimension of W?
We need to check.
Right, we need to check. It's tempting to say, well, 3, right? There are 3 elements here, but they're not necessarily linearly independent. Okay, and it's not obvious just by looking at them, because for 3 guys to be linearly independent, it's not enough that one is not a multiple of the other. Maybe this guy is 6 times this minus 5 times this. Okay, we don't see that automatically. So only after we verify if they're linearly independent, or maybe not, will we know what is the dimension of W. Clear? That's important. So W, these 3 guys are a spanning set for W, but they're not yet a basis because we don't know linear independence. Okay, so we have to check that. So we need to check linear independence. Clear? How do we check linear independence? This is something we've done several times. For example, we can straighten these out as rows of a bigger matrix, right, a 3 by 4 matrix, and start doing row operations until we reach an echelon form. If there's a row of zeros, then they're not linearly independent. If not, then they are. Let's do that. So I'm straightening them out as rows of this matrix. So it's 1, 2, 3, 4, 1, 0, 0, 5, and 1, 4, 6, 3. And now I'm doing these row operations. You can check. R2 is R2 minus R1. R3 is transforms to R3 minus R1. And I get the matrix 1, 2, 3, 4, 0, negative 2, negative 3, 1, and 0, 2, 3, negative 1. Do you agree? Good? And then one more step, R3. Let's do it here. R3, I'm going to take it to be R3 plus R2, and I get the zero row. Right? So since there's a zero row here, only these two rows are linearly independent. Remember, the non-zero rows in a matrix in echelon form are linearly independent, right? You can see that directly because one is not a multiple of the other, right? So these two are linearly independent, meaning that R3 in the original one was extra, right? Because we managed to annihilate it, right? So only these two were sufficient to span everything. This one was a linear combination of the other two. Okay, and in a previous example that we did some time ago, we even saw how to trace the exact scalars by which this is a linear combination of these two. Remember we did that? Okay, so the conclusion is that those three matrices that we started with are linearly dependent. The third one is not necessary, and BW, which is the set containing only the first two, 1, 2, 3, 4, and 1, 0, 0, 5, is a basis for W, implying that the dimension of W is also 2. Good? It's a basis because these two are linearly independent. Okay, you can take these two. That would be just as good, right? So these two are linearly independent, and they span everything. Good? Everybody good? Okay, so what can we say in general about dimensions and bases for subspaces? Well, we said one thing, that if you take a basis for a subspace, for example this, we can complete it into a basis of the entire space. And if I'm not mistaken, this is precisely the example that we did in the previous lesson. Take a quick glance at which example we did. I think this is precisely what we did.
It was 6.
Yeah, we used 6.
It was 1, 2, 3, 4, and 1, 0, 0, 6.
Yeah.
Oh, well. Okay, so we know how to do that. But there's a theorem here that is useful, and let's write it. There are a couple of them. So here's the first theorem.
Basis of the set of subspaces smaller or equal to the...
Very good, very good. So if U is contained in V, if U in V is a subspace, a vector subspace, then the dimension of U is less than or equal to the dimension of V. And furthermore, and the dimension of U equals the dimension of V if and only if U is all of V. Okay? So let's prove this. Okay? It should sound extremely obvious. It should make sense. Okay? You should think, wait, there's no way that the dimension of U is greater than the dimension of V, because that would mean that U lives inside V, and somehow I took a basis for U inside V, which has more than n elements, right? And it's a spanning set. That's a contradiction. We know that the greatest number of elements in a spanning set in V is at most n, right? Do you agree that that makes sense? Okay, that's the proof. That's precisely the proof. Okay, so let's write it down. If the dimension of U were greater than the dimension of V, okay, and we're going to reach a contradiction, then a basis for U is a linearly independent set with more than n equals dim v elements. Right? Because it has dim u, which is greater than dim v elements, and that cannot be. It's living inside v. We had a theorem. A linearly independent set could have at most n elements. Okay? So linear with more than n equals dim v elements, in contradiction to the previous theorem. The previous theorem in the previous lesson. So it was part 4, in contradiction to part 4 of the previous theorem. Okay, good? Okay, so this proves up to here. The dimension of U has to be less than or equal to, because if it's greater than, we reach a contradiction. But now, why are they equal? Well, this is an if and only if statement, so we need to prove two things. If U equals V, obviously they have the same dimension because they're the same thing. So this direction really is a trivial statement. There's nothing to prove. What we need to prove is this, that if the dimension of U equals the dimension of V, then they're the same space. Okay? And this is, it's not hard, but it's not a trivial statement. All we know is that these two things have the same number of elements in a basis. That's all the dimension is. Why does it force them to be precisely the same thing? Why can't we find a four-dimensional subspace inside V, which is not all of V? Okay, clear? Is it clear why there's still something to say in this direction? Okay, so by part 2 of the previous theorem, so part 2 of the previous theorem said that every linearly independent set with n elements is a basis. Okay, so by part 2 of the previous theorem, if the dimension of U equals the dimension of V, then a basis of U, suppose the dimension of U equals the dimension of V. Take a basis for U. It's going to have n elements, right? The dimension of V we denoted by n, it's going to have n elements. Then a basis of U has n elements, right? And part 2 of the previous theorem said it's a basis, it's linearly independent with n elements, it's a basis for everything, it's a basis for the entire space. Okay? Has n elements and is thus a basis for V. Good? So we started with a basis for U. It has n elements. Therefore, it's a linearly independent set inside V. U lives inside V with n elements. Therefore, it's a basis for V. So anybody in V is already in U, right? Because it's generated by a basis for U. Okay, so V equals U. Hence, U and V coincide. Anybody in V is already in U, so V is contained in U, and a priori U was contained in V, so the sets are equal. Good? Follow the logic? Okay, so this is the first theorem that we have. This completes the proof.
Could you specify why did you have to write the dimension of U is smaller or equal than the dimension of V and equals? Why did you
There are two statements here.
That's
The first statement is this one. The dimension of U is less than or equal to the dimension of V. That's one statement, and the proof ended at this point. Okay? Then there's a further statement, which is not the same thing. If they're the same, then, or if and only if they're the same, then the spaces are the same. Meaning, what the practical meaning of this is that if you look back at our example, for example here, V was 2 by 2 matrices over R. You cannot have a subspace of dimension 4 in V that's not everything. You cannot have a strict subspace, an honest subspace, that is 4-dimensional. If you found a subspace that's 4-dimensional, it's everything. Okay? Clear? Okay. Okay. So here's the next theorem. The next theorem I'm not going to prove. The proof is lengthy and has a lot of, it's very technical, and I'm going to skip the proof of the next theorem. However, I do want to write it. It's a useful theorem, and it relates to sums of subspaces. Remember, we had the notion of a sum of subspaces? Okay. Okay. And it's the following theorem. Before I write it, I want to tell you the idea. So let's start, and then I'll draw a little sketch here. Let U and W in V be subspaces. Now, think of sets for a minute. It's hard to draw subspaces because it's hard to draw the operations. How do we draw the fact that A plus B lives inside the subspace? It's easy to draw A and B live inside the subspace, but how do we draw that A plus B? Where do we draw A plus B? Okay? But it's easy to draw sets. So suppose we have a big set. Here's V as a set. Okay, let's not call it V. Let's call it A as a set. And suppose we have two subsets here. This is the subset B, and here we have a subset C. Okay, and now we're just thinking of the number of elements. Okay, suppose B has X elements, and C has, let's say, Y elements. Okay? So, how many elements are there in B union C?
X plus Y.
No.
Well, it's the or less.
That's the maximum.
Not or less, necessarily less, because you're counting these guys twice. Do you agree? I'm asking how many elements are in the union, in this entire figure 8 here. Okay? So they're all the elements, the X elements of B.
Minus the 0.
No, these are just sets. Yeah. There are some guys, here's one, here's another, here's a third one. There are some elements that belong to both. That's what this drawing indicates, that there is an intersection. Okay? So the number of elements, let's use this notation. The number of elements in B union C equals the number of elements in B plus the number of elements in C. But if we just do that, we're counting these guys twice. Do you see that? Minus the number of elements in B intersection C. Do you agree? Is this clear? Okay, and here we're just looking at sets with elements. That's it. So if this is the number of elements in B union C is x plus y minus the number of elements in the intersection. Clear? Everybody? So this is precisely the statement that's going to be written here, but it's not going to be in terms of the elements of the vector spaces. It's going to be in terms of the generators, in terms of the dimensions. If you take a big space V, and you take a subspace U and a subspace W, the dimension of U and the dimension of W, this big thing, the union, well, the union is not necessarily a subspace. Remember we said that? Okay? But the sum is a subspace, and the number of element, the dimension of the sum is the dimension of U plus the dimension of W minus the dimension of the intersection, which I'm counting twice. Okay? So that's where the idea comes from. And you'll see formulas like this appear in many places in mathematics. Okay? And they always have the same flavor, but here it's going to be in terms of the dimension. Okay? So is the idea clear? Again, I'm not going to prove it because the proof is technical. The proof requires a lot of time and a lot of concentration, and I'm not convinced that it's worth that time in as far as your needs go. Okay, you're not mathematicians after all. Okay.
Notation wrote for the I don't know how to say the lines. Is it for numbers or number of elements?
Just a number of elements. Okay. So let U and W be subspaces. Then the dimension of U plus W, this is a subspace, okay? It's all the guys of the form little u plus little w, right? Equals the dimension of U plus the dimension of W minus the guys that I counted twice, the dimension of U intersection W, and this again is a subspace. It makes sense to talk about its dimension. Okay, clear? Okay, so this is part 1 of the theorem. And part 2, remember we had the notion of a direct sum? A direct sum of spaces, we denoted it with a circle around the plus, was the situation where there was no intersection. Okay? So by definition, a direct sum was a sum where each vector can be written in only a unique way. Remember that? And then we had a theorem that a sum is a direct sum if and only if there's nobody in the intersection except the zero vector. Remember that? Okay, so U plus W is a direct sum denoted, this is just a reminder, U plus W, if and only if, and this is going to be pretty obvious if you believe part 1. Part 1 is what requires a lot of proof. If and only if the dimension of U plus W equals the dimension of U plus the dimension of W. Because if it's a direct sum, here's the proof of 2. I'm saying the proof of 2 out loud. A sum is direct if and only if the dimension of the intersection, well, the intersection is just the zero vector, and therefore the dimension of the intersection is 0. Right? There's no non-zero vector in a basis for the zero subspace. Okay? So this becomes nothing, and you get this. Okay? So sometimes you'll see it as a statement that the dimension of U plus W is the dimension of U. Maybe we'll write that as to... So this goes along together. Okay? 'Cause If u plus w is not a direct sum, then this does not hold. Okay, only you do need the intersection. Okay, good? Clear? Okay, so I'm not proving these things, but I do want to do examples, of course. So let's do an example. So in fact, I used u rather than w. Okay, let's erase this and do an example. So example. Let's take V again to be 2 by 2 matrices over R. And let's take two subspaces. So U is going to be the subspace that we had before. All the matrices of the form A, B, minus B, A plus B. So this is an example we considered earlier. Okay? And W is going to be all the matrices satisfying that they coincide with their transpose. Do you remember what we called a matrix like this? Symmetric. All the symmetric matrices. Okay? So let's study. Let's understand what is U, what's the dimension of U, what is W, what is the dimension of W, what is U plus W, what's its dimension, what is U intersection W, what's its dimension. Okay, let's study all the different possibilities here. So let's start with U. We know, we have seen, just not a long time ago, that the dimension of U is 2, and that the set 1, 0, 0, 1 and 0, 1, negative 1, 1 is not just spans, as a basis for you. And we even called it BU. Let's call it BU again. Good? Remember this? Okay. What about W? What about W? So W is all the matrices of the form A equals A transpose. This I can rephrase in a similar manner to this. Okay, so a general element in W, so this is U. W. So a general element, a general matrix in W is what? A and C can be anything, and being symmetric imposes that B here has to be the same as B here. Do you agree? That's the property of being symmetric. When you do the transpose, you get the same thing. Do you agree? Okay. Therefore, I can write this as A times 1, 0, 0, 0 plus B times 0, 1, 1, 0 plus C times 0, 0, 0, 1. Do you agree? So a basis for W is the set 1, 0, 0, 0, 0, 1, 1, 0, and 0, 0, 0, 1. Okay? Well, I said this is a basis. Let's call it BW. But that requires some justification, because just having written it like this is only the statement that it's a spanning set, right? Every element here is A times this plus B times this plus C times this. So this set spans W. In order for it to be a basis for W, I need to show that they're linearly independent, right? So this set is a spanning set, or spans W. Spans W. And why is it linearly independent? Well, we know how to do it. We straighten them out as rows in a bigger matrix, and then it's already in echelon form. Let's show that. And is linearly independent since okay, that's true, but completely unnecessary, right? All we care is it in echelon form? Is there a zero row? That's all we care about in this case. So it's linearly independent since when we straighten it out as rows of a bigger matrix, 1, 0, 0, 0, 0, 1, 1, 0, and 0, 0, 0, 1, since this is in echelon form with no zero rows. Good? So BW is indeed a basis for W. So therefore, BW is a basis for W. And what is the dimension of W? Right. Good? Because the basis has 3 elements. Good? Everybody? Okay. So now let's talk about U plus W. So what is U plus W? It's all the elements in V, all the 2 by 2 matrix, which can be written as a sum of a matrix in U, of that specific form which defined U, plus a matrix in W, of that specific form which defined W. Do you agree? Okay. I can start understanding what a matrix like that would look like by kind of intersecting those restrictions. Okay, let's look back one board. What would a matrix have to satisfy in order to simultaneously be of this form and of this form? I can start understanding those conditions, and that's a legitimate approach. But I can say something else. Okay, I can say any element in U plus W is spanned by the union of these 2 bases, because it's something from U plus something from W. That's an element in U plus W. Something from U is a linear combination of these 2 guys. Something from W is a linear combination of these 3 guys. So something from U plus something from W is precisely a linear combination of these 5 guys. Do you agree? So BU together with BW is a spanning set for U plus W. Does everybody agree? Let me say it again. Something from U is a linear combination of these 2 guys, because that's a basis for U. Something from W is a linear combination of these 3 guys, because this is a basis for W. Something from U plus something from W is a linear combination of these 5 guys. Clear? Okay, so let's write that. Let's give them names, okay? Let's make life a bit easier by giving them names. So let's call this guy A1. Let's call this guy A2. This guy is going to be A3, A4, and A5. Okay? And now, let me write the set A1, A2, A3, A4, and A5. A1 and A2 were the basis for U. A3 through A5 were the basis for W. Spans U plus W. Does everybody agree to this? Can it be a basis?
No, because it is 5.
Right. It automatically is too big. It cannot be a basis because it has 5 elements, and we're working in an ambient space which is 4-dimensional. So a linearly independent set in V has at most 4 elements. So we automatically know that at least one of these is extra. At least. Maybe 2 are extra. Okay, we don't know that yet, but at least one is extra. Do you agree? So this spans U plus W. It is not linearly independent since the dimension of the the dimension of the ambient space is 4, and this has 5 elements. Okay, good. Okay, so how do we extract from this 4 guys, or maybe only 3, that are linearly independent? What do?
We put it in the matrix.
Right, we straighten these guys into rows of a big matrix and start doing row operations until we reach the echelon form. There's going to be at least 1 row of zeros there. Okay, so let's do that.
A1 is, you can break it out.
So what you're saying is that if sometimes, instead of just diving into the algorithm or the method for doing something, you can take a step back, look at it, and sometimes you can kind of make observations that would save you a lot of calculations. That's what you're saying, right? And you're saying, let's see if I agree, you're saying, let's look at these 5 guys, and what are you saying?
A1 is 3 plus 5.
A1 is A3 plus A5. Does everybody agree? So we can right away throw A1 out. Would that mean that necessarily these 4 are linearly independent? No. Maybe still there's some dependence going on here. Do you agree? Okay, so there's still, but I agree. This is always a good approach. I want to write the full matrix with the 5 rows. It's very easy. They're all zeros and ones here, so it's not going to be a lot of work. But I want to do it the long way, with your permission. Okay, so here are the 5 rows in the order that they appeared: A1, A2, A3, etc. So it's 1, 0, 0, 1, 0, 1, negative 1, 1, 1, 0, 0, 0, 0, 1, 1, 0, and 0, 0, 0, 1. This is A1, A2, A3, A4, A5, straightened out as row vectors in a bigger matrix. And now I want to do the row operation and reach the echelon form. So I'm going to do R3 goes to R3 minus R1, and R4 goes to R4 minus R2. In any lesson in Algebra 1, once per lesson you should do row operations on a matrix, right? It's kind of a therapy. Even if it's not necessary, if you're talking about something completely abstract, just take a matrix and do some row operations to calm down, right? If you're nervous because of something totally unrelated that has to do with, personal relations, politics, your car broke down, take a matrix and do some row operations. You'll feel calm, right? Okay. What do we get? Tell me if I'm not making any mistakes here. 1, 0, 0, 1, 0, 1, negative 1, 1, 0, 0, 0, negative 1, 0, 0, 2, negative 1, and 0, 0, 0, 1. And then I'm going to do R5 goes to R5 plus R3, and R3 I'm going to replace with exchange locations with R4, and I get 1, 0, 0, 1, 0, 1, negative 1, 1, 0, 0, 2, negative 1, and 0, 0, 0, negative 1, and then 0 rows. Good? Mistakes? Good? Okay, so this is echelon form. There's 1 row of zeros, right? So these guys are a basis for U plus W. We started with a spanning set the rows of A and the rows of B have the same span. That's a theorem that we had. This one's not necessary, so the span of these 4 rows is exactly the same as those. And this is a basis. I don't need to figure out which ones were the ones that were unnecessary, which ones did I throw out, right? I could start tracing, but this could be a process of 17 intermediate steps, and it could be very hard to trace. I don't need to, okay? So B, U plus W, which is the set of those 4 matrices, 1, 0, 0, 1, 0, 1, negative 1, 1, 0, 0, 2, negative 1, and 0, 0, 0, negative 1, is a basis for U plus W. The dimension of U plus W equals 4. And one further conclusion, U plus W is everything, right? Because of the second part of the theorem we had before. If you have a subspace with dimension the same as the ambient space, it's everything. U plus W equals V. Do you agree? Everybody? Okay. One more subspace that we want to study is the intersection of U and W. That's also a subspace. Let's do that. So for that, I'm going to resort to this theorem, which is here. Okay? So the intersection, I can, before doing anything, I can say how big the intersection is going to be. Right? One dimensional. Right? Because U plus W was 4-dimensional, right? So before I erase it, let's do this. Let's do this. Let's leave this. Okay. So now we're continuing the example, and we're looking at U intersection W. So the dimension of U intersection W is 1, since this we know by the theorem, and in our example, the dimension of U plus W was 4, right? That's what we just saw. The dimension of U was 2. The dimension of W was 3. Therefore, this has to be 1. Do you agree? This is a weird way of writing an equation. Let's just put the 1 here, but good? So we know that the dimension of the intersection is going to be 1. But that doesn't tell us what a basis for the intersection is. What is the intersection? Okay. By the way, is this a situation of a direct sum? No. Right? There is a non-trivial intersection. Okay? There are elements which are both in U and in W simultaneously. Okay? So it's not a direct sum. So we know that we're expecting something one-dimensional. How do we find a basis? So for this, we can, for example, look at what is an element that satisfies being both in U and in W. That's usually easier than satisfying being in U plus being in W. Okay, being a sum of something in U plus something in W. Being in the intersection is usually easier to observe. So look at this board for a second. Being at the intersection means it's simultaneously of this form and simultaneously of this form. That's what it means to be in the intersection. It's both here and here. Okay? So this puts only one restriction. The inverse diagonal elements should be equal. But this says that they're not equal. One is the minus of the other. And that doesn't leave much choice. B has to be 0. Do you agree? And there's no restriction on A. And C has to be of the form A plus B, but B is 0. So do you agree that elements in the intersection are merely what we call scalar matrices, A00A. Does everybody see that? So let's write it here. Indeed, elements in the intersection, in U intersection W, are of the form A00A, and a basis for U intersection W is merely the set 1, 0, 0, 1 is a basis. Good? Okay. So this is an example of it's not just an example, it's in fact a classical example. It's a very standard form of question that you will see a lot, even in exams and homeworks. And you kind of get a subspace, get another subspace, and are asked about the sum, the intersection. Is it a direct sum? Find the basis for the intersection, find the basis for the sum, and so on and so forth. Okay, so this is really a very standard sort of question in this context. Okay, questions? Everybody good? Okay, so this wraps up our discussion of bases and dimensions for subspaces. Coming up next is a further step towards the idea that we already are really getting a feeling for, that sometimes two seemingly different spaces are actually the same space in disguise. Okay? And that's coming up next in terms of the notion of a coordinate vector next time.